Hi student, welcome to this new video on basis and dimension. Remember, we said in the previous video that considering a subset S of a subspace V, S is a basis of V if and only if S is linearly independent or the vectors of S are linearly independent. Also, we say that S must span V or span S equals to V. Now, we also define the dimension. The dimension of a vector space is a number of elements in any of its bases. Okay, now let's have a look on some practicals. Example, find a basis and the dimension of the plane pi x plus 6y minus 9z equals to 0. How do we solve that? Okay, so the first thing that we should do, we need to write this in terms of matrix, right? And since this is a plane, so we have that the reduced row echelon form of this will be 1, 6, minus 9, 0, right? So if you observe this, you will see that we have variable x, y, z, right? And you see that x is a fixed variable and y and z are free. So we will have y equals to s and z equals to t. So this will lead to x, y, z. So from this equation, this reduced row echelon form, or this one, we have that x equals to minus 6y plus 9z, and y is s and z is t, which lead to x is minus 6s plus 9t, y is s and z is t, right? So this will lead to x, y, z equals to minus 6s plus 9t st, right? So this will give me s minus 610 plus t 901, right? So what do we have here? Remember that s and t are any scalar, right? So having said that, this will lead to the fact that pi, right, will equal to span of minus 610 and 901. You can call this V1, vector 1, and V2, right? So what do we get from here? We realize that the span of these vectors will give us every point on the plane, right? The span of these vectors will give us every point of the plane, right? So we can be sure that pi equal to span of V1 and V2. And now we need to see if this will make a basis. Now when we look at these two vectors, right, there will be a basis if these vectors are linearly independent. So if alpha V1 plus beta V2 equal to 0, right, alpha should be equal to beta should be equal to 0 for them to be linearly independent, right? So having that, we will have that is minus 6 alpha plus 9 beta equal to 0, and then we have alpha equal to 0 and beta equal to 0. So we have that alpha equal to beta equal to 0. So V1 and V2 are linearly independent, right? So therefore, you can say that the basis be V1, V2, right? So we can have that V1 and V2 constitute a base, right? So it means that these vectors, right, these vectors are generator of the plane. So, in conclusion, we can see that B is a basis of pi, right? And what's the dimension of pi? The dimension of pi is 2, because we define the dimension of a vector space as the number of elements in its basis. And we have 2 elements in the basis B, so the dimension will be 2. All right. Now let's have a look on another example, right? Example 2. Yeah, and that will make the deal for our video. Now, in this example, I want us to answer the question, right? Determine whether the set is a basis for R3, right? And then find the dimension. So, what is the set? We have that the set is equals to 1 0 minus 1, 2 1 minus 1, and minus 2 1 4. Okay, so as a solution, what do we have to do? What do we have to do here? What do you have to do? So you have to remember that for this set to be a basis for R3, first, the set must be linearly independent, right? And S must be a spanning set, right? Remember the 2 conditions that we gave for a subset to be a basis of a vector space. So let's check if they are linearly independent. So if it is a case, it means that alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3, right, should be equal to 0. So this leads to 1 0 minus 1, 2 1 minus 1, minus 2 1 4, right? Alpha 1 alpha 2 alpha 3, right, equal to 0 0 0. And we can write this in our augmented matrix form, right? So 1 0 minus 1, 2 1 minus 1, minus 2 1 4, dot 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 dot. Right. So we now need to apply the Gauss reduction method. So we need to have a 0 here, right? Here we already have a little entry 1. Here we have a little entry 1. So we need to have 0 below and 0 above. So the first thing to do over here is to replace the row 3 by row 3 plus row 1. Since we have minus here, minus 1 and 1 here, so it can make us 0 easily. Yes, we can have 0 there easily. So this will lead to 1 0 0, 2 1 1, minus 2, right? 1 2, dot 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 0 0 0. Now what next to do here? So we need to replace, to have a 0. We need a 0 here and a 0 here. So we need to do that R1 is replaced by R2 minus R1 minus 2 R2. That's 1. And then that also R3 is replaced by R3 minus R2. And this will lead to 1 0 0 0 1 0, right? Minus 4 1 and 1. Okay, so this is a leading 1. The leading entry is a leading 1, so we need to have 0 and 0. So what to do is that we will replace the first row again by row 1 plus 4 row 3, and then we also have that we replace row 2 by row 2 minus row 3, and this will lead to 1 0 0, right? And then 0 1 0 and 0 0 1. Okay, so what do we observe from here? We observe from here that it follows that from what we see, that alpha 3 will equal to 0, alpha 2 will equal to 0, and alpha 1 equal to 0. So alpha 1 equals to alpha 2 equals to alpha 3 equal to 0, which is the condition for the linear combination of the vector to be linearly independent. So hence S is linearly independent. dependent, right? So as S consists of 3, so as S consists of 3 linearly independent vectors, as S consists of 3 linearly independent vectors in R3, it must be a basis of R3. So what's the dimension therefore of S? Right? The dimension of S is 3, because we define the dimension as the number of elements in a basis. So thank you very much, student, for your kind attention.